Fine, let's start. The observable universe is 93 billion light-years across. Every galaxy we've ever cataloged, every star we've ever named, every planet we've ever pointed a telescope at, all of it fits inside that number. Everything we have ever seen, or measured, or imagined is in there. So, what's outside? Number 10. Dark flow. In 2008, a NASA astrophysicist named Alexander Kashlinsky was doing something fairly routine, analyzing 3 years of satellite data on galaxy clusters, mapping how things move, standard stuff. Then he noticed something that was not standard at all. Over 700 galaxy clusters spread across billions of light-years of space were all moving in the same direction. Not randomly drifting the way you'd expect from local gravitational interactions, moving together coherently. Like they were all being pulled or pushed toward a single patch of sky sitting between the constellations Centaurus and Vela. Kashlinsky's team crunched the numbers. They looked for something inside the observable universe massive enough to cause that kind of pull. A supercluster, a void, some enormous concentration of matter we'd missed. There was nothing. Nothing we can see could account for it. So Kashlinsky proposed the only explanation that fit the data. Whatever is causing this lies outside the observable universe entirely. Some structure so massive, a remnant from before cosmic inflation stretched space to its current scale, that its gravitational fingerprint reaches across billions of light-years and bends the trajectories of entire galaxy clusters. He called it dark flow. But here's the thing. The team couldn't even determine whether the clusters were being pulled toward the source or pushed away from it. They know the direction. They don't know the sign. Something out there is exerting a force on the largest structures in the known universe, and we cannot tell if it's attracting or repelling. Kashlinsky said, at the time, we never expected to find anything like this. That's the scientific version of saying we have absolutely no idea what we're looking at. The Planck satellite later tried to confirm the signal, and the results were inconclusive. Some teams found it, some didn't. The debate is still open, but the data from 2008 is real. 700 galaxy clusters all leaning in the same direction towards something we cannot see and cannot reach. Whatever it is, it knows we're here. We're the ones who don't know about it. Number 9. The Many Worlds of Hugh Everett. Most people have heard of parallel universes in the quantum sense, the idea that at every moment reality splits into multiple branches, each one playing out a different outcome. It's been in every sci-fi movie made in the last 30 years. It's almost a cliche now. What most people don't know is the story of the man who actually invented it. In 1957, a Princeton graduate student named Hugh Everett III published a thesis called Relative State Formulation of Quantum Mechanics. His argument was simple and devastating. The quantum wave function, he said, never collapses. When you measure a particle and it chooses an outcome, spin up or spin down, decayed or not decayed, it doesn't choose. Both outcomes happen. The universe branches. Both versions continue forward, each one real, each one unaware of the other. In the Everettian picture, right now, there are versions of you who made different choices this morning, who live in different cities, who are watching a completely different video. They're not metaphors. They're not thought experiments. They're real branches of the universal wave function, inaccessible to us but physically existing beyond the reach of any observation we could make. The physics community in 1957 was not impressed. Niels Bohr's Copenhagen interpretation was the orthodoxy, and nobody wanted to hear that the wave function never collapses. Everett's thesis was largely ignored. So Hugh Everett did something remarkable. He left physics entirely. He took a classified job at the Pentagon calculating nuclear targeting strategy for the Cold War, working out kill ratios, optimizing warhead deployment, applying game theory to the question of how to destroy civilization most efficiently. He never publicly discussed his theory again for the rest of his life. The man who proposed that reality branches into infinite parallel universes spent the rest of his career in a classified world, doing work he couldn't talk about, on problems nobody outside the government could see. He died in 1982. He was 51. His theory is now one of the most seriously considered interpretations of quantum mechanics among physicists working in quantum computing and quantum gravity. He never knew. The man who invented parallel universes, and he never got to live in the one where he was right. Number 8, the Big Bang was a collision. Here's the standard story we tell about the Big Bang. There was a singularity, an infinitely dense point. It expanded. Space stretched. Matter cooled. 14 billion years later, here we are. It's a good story, but it has a problem. A singularity, a point of infinite density, is where our physics breaks down completely. The equations stop working. We can describe everything after the first fraction of a second, but the moment of the bang itself is a black box. A mathematical wall. In 2001, physicists Justin Curie, Bert Overoot, Paul Steinhardt, and Neil Turok proposed tearing that wall down and replacing it with something far stranger. Their model, called the ekpyrotic universe, begins with a different premise. Our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space they call the bulk. And it is not alone in there. Floating nearby, separated from us not by ordinary space but by a microscopic gap in a fourth spatial dimension, is another brain, another universe. For most of cosmic time, these two brains just drift. Cold, nearly empty, slowly attracting each other through gravitational forces acting across that tiny gap. And then they touch. The collision releases an enormous burst of energy. Matter and radiation flood into both brains. Physics cranks up from near zero to unimaginably hot in an instant. That collision is what we call the Big Bang. But here's the thing. Steinhardt and Turok then extended this into a cyclic model. Our universe expands, ages, cools, just as we observe. And dark energy, that mysterious force currently accelerating the expansion of the cosmos, is not a cosmological constant embedded in the fabric of space. It's the slow gravitational pull of the other brain, drawing us back, setting up the next collision. Our universe's ultimate fate and its next beginning are the same event. The Big Crunch and the Big Bang. One moment. We are somewhere in the middle of a beat, and we have no idea how many times this has already played out before the universe we were born into. Number 7. Searching for bruises from another universe. If the universe we live in is a bubble, one of countless bubble universes that inflated out of an eternally expanding primordial foam, then, at some point in the early history of our universe, another bubble might have collided with ours. Not a catastrophic collision. More like two soap bubbles touching. A glancing impact early on that left a circular imprint, a temperature scar, on the cosmic microwave background. The oldest light we can see. The photograph of the universe when it was 380,000 years old. In 2011, a UCL PhD student named Stephen Feeney wrote the first algorithm specifically designed to look for those scars. He and his colleagues searched the 7-year WMAP dataset, the most detailed map of the CMB we had at the time, looking for circular anomalies consistent with what a bubble collision would leave behind. They found 4. 4 candidate signals. 4 circular patches in the oldest light in the universe that match the predicted signature of a collision with a neighboring bubble universe. But here's the thing. The data wasn't clean enough to confirm them. The signals were interesting and statistically worth noting, but they sat right at the edge of what the dataset could resolve. Feeney's team constrained the upper bound on detectable bubble collisions. They set a limit, but they could not say, yes, those 4 are real. They couldn't say they weren't either. Planck satellite data later attempted a cleaner look. The signals weren't confirmed, which means one of two things. Either the universe has no bruises because it never collided with anything, or the bruises are real, and our instruments just aren't sharp enough yet to be certain. 4 marks in the oldest photograph we have of the universe. We don't know what made them. We might never know. Number 6. Universe Darwinism. Why does our universe have the physical constants it has? Why is gravity this strong? Why does the Higgs field have this particular mass? Why does the strong nuclear force operate at this specific range? If you shift any of those constants by even a small amount, the universe collapses before galaxies can form, or matter can't hold itself together, or stars burn out in seconds. We appear to live in a universe that is extraordinarily, suspiciously fine-tuned for complexity to exist. The usual explanations are two. Either someone designed it that way, or we're in an infinite multiverse where every combination of constants is realized somewhere, and we simply find ourselves in one that works because we couldn't exist in any other. In 1992, physicist Lee Smolin proposed a third option, and it is arguably the strangest of the three. Every black hole, Smolin argued, gives birth to a new universe inside it, not metaphorically, physically. On the other side of the singularity, beyond the point where our physics breaks down, a new region of space-time inflates into a fully formed universe, and that daughter universe inherits the physical constants of its parent with small, random mutations. Now run that process across cosmic time. Universes that produce more black holes have more offspring. Universes that produce fewer black holes have fewer. Over many generations, across an uncountable family tree of universes, the ones with constants optimized for black hole production become statistically dominant. Our universe is extraordinarily good at making black holes. Hundreds of billions of them confirmed so far. Under Smolin's model, that's not a coincidence. That's a fitness trait. We're the descendants of a long line of successful black hole producers. Smolin explicitly compared himself to Darwin. Darwin proposed natural selection without knowing the molecular mechanism of inheritance. That came 60 years later with DNA. Smolin proposed the same structure for universes. The reproductive logic is there, but the mechanism by which physical constants are transmitted through a black hole singularity is still unknown. He called it cosmological natural selection. And he made a specific testable prediction. No neutron star should exceed approximately 2 solar masses, because a universe optimized for black holes would make that mathematically unlikely. In 2019, astronomers confirmed a neutron star at 2.08 solar masses. Smolin's theory is under pressure, but it hasn't broken yet. And the idea it planted, that the universe you're sitting in right now is one generation in a cosmic family tree stretching back through black holes and universes you will never observe, that idea is still out there, waiting to be proven or killed. Number 5. The bubble that ends everything. In physics, the word vacuum doesn't mean empty, it means the lowest energy state of a field. The floor. Except our floor might not be the actual floor, it might be a ledge. If the Higgs field, the field responsible for giving particles their mass, is in a metastable state rather than a true ground state, then our universe is sitting in a false vacuum. A local minimum, not the deepest possible configuration of energy, just a dip. And like a ball balanced on a ledge, it can fall. Spontaneously, anywhere in space, a quantum fluctuation could nucleate a tiny bubble of true vacuum, the real floor. A region where the Higgs field collapses to its actual minimum energy, rewriting the laws of physics inside it. The mass of every particle would change. The forces would change. Chemistry, matter, structure, all of it instantly invalid. That bubble would expand at the speed of light. It would not slow down. There is no force that would stop it. It would consume space itself as it moved, converting everything it touched into a region where our physics no longer exists. Now, the Higgs boson measurement in 2012 placed the Higgs mass in a range consistent with metastability. Not confirmed metastable, but consistent with it. The parameters sit uncomfortably close to the boundary. But here's the thing. If a true vacuum bubble exists right now and is expanding toward us, we will never see it coming. It travels at the speed of light. It destroys the very space ahead of it. There is no signal, no light, no wave, no warning that can outrun it and reach us first. The absence of evidence is not evidence of absence, because evidence cannot arrive before it does. Sidney Coleman, one of the physicists who formalized this theory, described vacuum decay as the ultimate ecological catastrophe. He was being wry, but he wasn't wrong. Somewhere out there, maybe billions of light years away, maybe much less, the conditions for this might already exist. and the universe we know would end not with fire or cold or collision, but with a change in the rules. Instant, silent, complete. Number 4. A photograph of the universe before ours. Roger Penrose won the Nobel Prize in Physics in 2020 for his work on black holes. He is one of the most mathematically rigorous physicists alive. And for the last 20 years, he has been arguing something that most of his colleagues consider extraordinary. He thinks he's found evidence of the universe before ours, in the sky. Penrose's theory is called conformal cyclic cosmology. The idea is this: our universe began with a Big Bang, expanded, and will eventually reach a state where all matter has fallen into black holes. Those black holes will then evaporate through Hawking radiation, the slow thermal bleeding of energy that Stephen Hawking predicted, over a timescale so large it's almost meaningless to say. Roughly 10 to the power of 106 years. That's a 1 followed by 106 zeros. The current age of the universe is about 10 to the power of 10 years. We are nowhere near the beginning of that process. When every black hole has evaporated, what remains is a universe of pure radiation. No mass, no structure. And here's Penrose's key insight. A universe of pure massless radiation has no meaningful sense of scale. Seconds and light years become mathematically equivalent. Time, as we experience it, effectively ceases to have meaning. And that scaleless end state, Penrose argues, is mathematically identical to the beginning of the next Big Bang. The end of one aeon becomes the start of the next. Seamlessly, conformally, not a singularity, a crossover. Now, when those black holes were evaporating in the previous aeon, taking unimaginable amounts of time to bleed out their last photons, Penrose predicted they would leave a faint circular imprint in the radiation that crosses over into our universe. A hotspot. A ring. The compressed dying breath of a supermassive black hole from a universe that ended before ours began. He called them Hawking points. In 2020, Penrose and his colleagues published a paper in the monthly notices of the Royal Astronomical Society claiming they had found these Hawking points, anomalous circular hotspots in both the Planck and WMAP-CMB data at 99.98% confidence. Independent teams have since challenged the statistical analysis. Most cosmologists remain skeptical. The signals, they argue, are consistent with standard cosmic inflation once you account for the look elsewhere effect, the statistical inflation that happens when you search for a pattern in a large dataset and find it. But Penrose has not conceded. As recently as March 2025, he and his colleagues published a further refinement of the theory. When you look at the oldest light in the universe, that faint thermal glow left over from 380,000 years after our Big Bang, you are, according to Penrose, looking at something that contains the compressed final emissions of black holes that took longer to die than the entire lifespan of any universe we can imagine. There may be photographs of the previous universe in our sky. Faint, circular, hot. We just can't agree yet on whether we're seeing them or imagining them. Number 3. Inflation forces the multiverse into existence. In the early 1980s, Alan Guth at MIT and Andre Linde at Stanford, independently around the same time, proposed cosmic inflation. The idea that in the first fraction of a second after the Big Bang, the universe expanded at a rate far exceeding the speed of light, stretching from subatomic scales to something approaching its current size in a moment so brief it doesn't have a useful comparison. Inflation solved multiple problems simultaneously. It explained why the universe is geometrically flat. It explained why the CMB temperature is almost identical in all directions, even though without inflation, opposite sides of the sky were never in causal contact with each other. It explained why we don't see magnetic monopoles everywhere. Inflation is not fringe cosmology. It is the mainstream. Most working cosmologists accept something like it happened, and that's where things get uncomfortable. Because once you accept inflation, you almost mathematically force something else into existence alongside it. Eternal inflation. Inflation is driven by a quantum field, and quantum fields fluctuate. Even as our patch of space stopped inflating, the fluctuation that produced our universe settling into the hot Big Bang, other regions of that inflating field kept going. Quantum fluctuations in those regions prevented them from settling. They kept stretching faster than light forever. Inside that eternally inflating foam, other quantum fluctuations produce other bubble universes, each one inflating into something the size of what we call the observable universe, or larger. Each one potentially with different physical constants depending on how the underlying fields settle. André Linde, who has spent decades refining this picture, estimates, when combined with string theory's landscape of possible vacuum configurations, that the number of distinct possible universes this process could produce is 10 to the power of 10 to the power of 16. That number doesn't have a name. It is so large it cannot be visualized. Written out in full, its digits would fill a volume of space larger than the observable universe. But here's the thing. You don't get to accept inflation and then politely decline the multiverse. They come together. The mechanism that makes our universe smooth and flat also makes it one bubble among an infinite, eternally self-reproducing foam of other universes. Paul Steinhardt, one of the original architects of inflation, has spent recent years trying to kill the theory for this very reason. He considers the multiverse an untestable monstrosity that inflation dragged in through the back door. Linde disagrees. He thinks the landscape of possible universes is the most natural prediction the theory makes, that the embarrassing thing isn't the multiverse, it's that we ever thought there would only be one. This is not a debate between science and speculation, it is a debate between two Nobel-caliber physicists about what science is allowed to say about things we cannot observe, and it has no resolution yet. Number 2, the universe is a hologram. In the mid-1990s, physicists Gerard 't Hooft and Leonard Susskind proposed something that sounds like a late-night thought experiment, but turned out to be one of the most rigorously supported ideas in modern theoretical physics. Everything inside a region of space, they argued, in every particle, every force, every event, can be completely described by information encoded on the two-dimensional surface surrounding that region, not approximately. Exactly, the three-dimensional volume is, in a precise mathematical sense, equivalent to the two-dimensional boundary. This is the holographic principle, and it didn't come from staring at the universe, it came from black holes. The problem was this: if you throw a book into a black hole, the information in that book, every word, every sentence, every quantum state of every atom, appears to be destroyed when it crosses the event horizon. But quantum mechanics forbids information from being destroyed. It's one of the foundational rules of the theory. So where does the information go? 't Hooft and Susskind propose that it doesn't go in. It gets encoded on the surface of the black hole. The event horizon, a two-dimensional surface, stores the complete information of everything that ever fell through it. The inside of the black hole is, in a sense, a projection of what's written on the outside. In 1997, Argentine physicist Juan Maldacena published a paper that formalized this into an exact mathematical correspondence. A five-dimensional universe with gravity is mathematically equivalent to a four-dimensional universe without gravity on its boundary. The two descriptions encode the same physics. Neither is more real than the other. That paper has over 10,000 citations. It is the most cited paper in high-energy physics. An entire generation of theoretical physicists has built careers on the implications. Now, extend this idea outward. Our observable universe has a boundary, the cosmic horizon, the furthest surface from which light can ever reach us. The holographic principle suggests that all the information describing everything inside that boundary, every galaxy, every atom, you, this moment, this sentence, could be completely encoded on that two-dimensional surface at the edge. Not stored there. Encoded there. The interior could, in a rigorous sense, be a higher dimensional projection of what's written on a surface we will never see. But here's the thing. This theory was not built to describe the universe. It was built to solve a problem about information falling into black holes. The implication that we might all be living inside a holographic projection was not the goal. It was a side effect of solving a different problem entirely. Maldacena himself has acknowledged that his mathematical correspondence applies to an anti-de Sitter space, a universe with negative curvature, while we appear to live in a de Sitter space with positive curvature. Extending holography to our actual universe is an open problem. So, we have the most mathematically supported idea in modern theoretical physics, which implies a stunning thing about the nature of reality, and it might not apply to us. Or it might apply perfectly. And we wouldn't know the difference because a perfect projection of a three-dimensional reality and the three-dimensional reality itself feel identical from the inside. You are sitting somewhere right now reading or listening to this, and we genuinely do not know whether the room you're in is three-dimensional or whether it is a projection of something written on a surface at the edge of everything. Number 1. All of mathematics is real. Everything on this list so far has assumed one thing: that there is a universe, some physical substrate, and that theories describe it. That mathematics is the language we use to model reality, not reality itself. MIT cosmologist Max Tegmark thinks that's the wrong way around. In a 1998 paper, and then at full length in his 2014 book, Tegmark proposed what he calls the mathematical universe hypothesis. The claim is this: physical existence and mathematical existence are the same thing. There's no difference between a mathematical structure and a physical universe. Every mathematical structure that is internally consistent, that can be described without contradiction, exists physically, somewhere. Not as a metaphor, not as a useful model, as a physical reality. This goes far beyond anything else on this list. An eternal inflation multiverse gives you universes with different physical constants. Smolene's cosmological selection gives you universes born from black holes. Everett's many worlds gives you quantum branches diverging from our own. Tegmark's framework gives you universes governed by entirely different mathematics. Universes where the rules of logic are different. Where time is not a dimension, where space has 7 axes instead of 3, or none at all. Every possible consistent mathematical structure, an infinite library of realities, each one as physically real as the one you're in, all existing simultaneously, all populated by observers who are asking the same question you're asking right now. Our universe is not privileged. It is one structure among an incomprehensible infinity of structures. The reason we observe the laws of physics we do is not that they were chosen or fine-tuned. It's simply that we are mathematical patterns complex enough to be self-aware, inside a mathematical structure complex enough to contain us. The question, why does our universe exist, dissolves. Why wouldn't it? The real question would be, why a consistent mathematical structure would fail to exist. And there's no good answer to that. Critics, serious ones, push back hard. George Ellis, one of the great cosmologists of the 20th century, has written that the mathematical universe hypothesis is completely untestable and therefore not science in any meaningful sense. Edward Frankel called parts of Tegmark's book mysticism. The line between a radical theory and a philosophical assertion is precisely where this debate lives. But spend a moment with the implications before dismissing them. If Tegmark is right, the question of what exists outside the observable universe is not answered by dark flow, or bubble collisions, or quantum branches, or holographic surfaces. It's answered by asking, how much mathematics is there? And the answer is, all of it. Everything that can be consistently described, all the structures, all the geometries, all the logics, all the observers wondering why they exist. You are a self-aware pattern in one mathematical structure among an infinite library of mathematical structures that are all, in a very precise sense, equally real. And somewhere in that library is a structure that contains no version of this question. Because in some mathematical universes, nothing ever gets complex enough to ask. That we got here, to this question, in this particular structure, is either the most ordinary thing in the world, or the only thing that was ever going to happen. We just can't tell which. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.